What if the next revolution in computing is not about making today's computers smaller or faster, but about building a completely different kind of computer? A machine that works using the strange rules of quantum physics itself. That is the story of quantum computing, one of the boldest ideas in the history of technology. NIST explains quantum computing around the core ideas of qubits, superposition, entanglement, and interference, which makes this an enduring scientific topic rather than a passing trend. To understand quantum computing, first remember how ordinary computers work. Classical computers use bits, 0 or 1. Quantum computers use qubits. And qubits can behave in ways ordinary bits cannot, thanks to superposition and entanglement. That does not mean quantum computers replace everything. It means they may handle certain kinds of problems in ways classical systems struggle to match. NIST's explanation makes exactly that distinction. The roots of quantum computing go back to the deeper discovery that nature itself does not behave like a classical machine. In the 20th century, quantum mechanics revealed a world where particles could exist in multiple possible states and influence each other in surprising ways. Then, in the early 1980s, the conversation changed. If nature is quantum, maybe the best way to simulate nature is with a quantum computer. That insight helped launch the field. IBM's learning material also frames this early era as the point where quantum theory began turning into a computing vision. For a while, quantum computing sounded almost philosophical. Then came the moment that made the world pay attention. In the 1990s, researchers showed that a sufficiently capable quantum computer could solve some problems far more efficiently than known classical methods, especially problems tied to factoring large numbers. That mattered because modern encryption relies heavily on those problems being hard for normal computers. But proving something in theory is very different from building it in real life. And that is where the next phase began: hardware. Researchers started trying to create qubits using real physical systems, superconducting circuits, trapped ions, photons, and other approaches. The hardware may differ, but the challenge stays the same. Can you create, control, and measure quantum states reliably enough to compute with them? Here's the part many people miss. The biggest enemy of quantum computing is not lack of intelligence. It is noise. Qubits are fragile. Tiny disturbances, stray fields, temperature changes, even cosmic rays can disrupt quantum states and ruin calculations. NIST specifically notes that these effects can destroy superposition or entanglement and force qubits to behave like ordinary bits. So the race in quantum computing is not just about making more qubits. And that is why error correction became one of the most important chapters in quantum computing. The goal is simple in idea, but difficult in practice. Combine many imperfect physical qubits so they can protect more reliable logical information. That is how the field aims to move from fragile demonstrations to useful, fault-tolerant systems. IBM's roadmap now places fault tolerance at the center of the next era, showing just how essential this step has become. So, where are we today? We are in the era of real quantum hardware, but still on the road toward large-scale, fault-tolerant quantum computing. That means the field has advanced a lot, but it is still being built. This is the honest, evergreen way to understand it. Quantum computing is not a finished consumer revolution. It is a major engineering frontier. Quantum computing matters because it could become powerful for certain kinds of problems that fit its nature. Not everything, not all software, not your daily spreadsheet, but fields like simulating molecules, understanding materials, exploring certain optimization tasks, and reshaping long-term cryptography are why this technology matters so much. Now, yes, people often connect quantum computing with AI, but the deeper truth is bigger than that. Quantum computing does not need AI hype to matter. Its importance comes from being a new computing paradigm in its own right. In fact, quantum computing is already influencing the present, even before fully fault-tolerant systems arrive. Why? Security. NIST finalized its first 3 post-quantum cryptography standards in August 2024 to help prepare systems for a future where powerful quantum computers could threaten current public key methods. That means quantum computing is not just a future story. It is already shaping how governments and organizations prepare for tomorrow's digital security. So the evolution of quantum computing is really the story of an idea that began in physics, grew through mathematics, faced the brutal reality of engineering, and is now pushing the boundaries of what computing can be. Not a fad, not a gimmick. A serious attempt to build machines that compute using the deepest rules of nature itself. And that is why quantum computing remains one of the most important long-term stories in technology. Subscribe for more deep but easy to understand tech stories, where we explain how the digital world really works without the hype.